Have you ever wondered if an ordinary person, by simply studying diligently, could visualize these complex things the way I do? And the answer is yes, because I am also just an ordinary person who has continuously strived to learn. In reality, there are no inherently extraordinary individuals. They are simply people who happen to find a passion for this field and dedicated time to acquire all related knowledge. They are just ordinary people like everyone else. They don't possess any innate talent or superhuman ability that helps them understand quantum mechanics or easily visualize electromagnetic fields without going through diligent training, reading, learning, and research. So, if you pick an ordinary person, but one who is willing to invest countless hours and effort into studying, working, deep thinking, and mathematical research, could that person become an outstanding scientist? Absolutely. When I'm truly immersed in my work, exploring the profound concepts, deep problems, and mysteries that I constantly ponder, I find it difficult to fully express them in words. Can you imagine? It's exactly like trying to ask a centipede which leg it moves before which. Everything happens so incredibly fast that I can't be sure exactly which ideas are flashing by or which processes are operating in my mind. However, I know for sure that it's a complex combination of differential equations, the process of solving them, and some kind of visual image of what's happening just as the equations indicate. But those elements are not clearly distinct, like the words I'm using to describe them. It's actually a rather strange and incredibly difficult experience to put into words. I wonder if trying to describe this is really useful, but I must admit that this is a very peculiar phenomenon that has particularly captured my attention. How different are the things that happen in each person's mind? I suspect they can be very, very different. When images, whether real or semi-real, appear in the mind, and we communicate with each other at profound, complex levels, seemingly conversing very harmoniously and understandingly, in reality, a huge translation diagram is silently at work. It converts one person's words into distinct, very different images in each of our minds. I discovered this very early on, at a very basic level. I won't go into detail, but I became fascinated with doing some experiments to find out something about our human perception of time. So I conducted an experiment myself. I would count, trying to count for exactly 1 minute. More specifically, I would count to 48, and I considered that to be 1 minute. Therefore, I would adjust myself and count 1 minute to 48, while still thinking I was counting seconds. However, that number was close enough to reality, and the interesting thing is, if you repeat this process, you can count very accurately to 48 or 47 or 49. The deviation is negligible. You'll find yourself very close to the 1 minute mark. And from that, I would try to discover what factors influence that perception of time, as well as whether I could perform any other activities simultaneously while counting. Have you ever wondered about your own capabilities? I've discovered that I can accomplish a great many things. However, not everything is easy. There are times when I face countless challenges, such as when I was a university student, one of the tasks I had to take on myself was laundry. Can you imagine even hanging socks became a problem? I needed to make a list to know exactly how many socks there were. Even though there were only about 6 or 8, I couldn't count them. The reason was that my counter was busy, and I couldn't determine the quantity until I found a method, arranging them according to a certain pattern to recognize the total number. After much practice, I discovered a unique technique. Thanks to it, I could read lines of text in newspapers by looking at them in clusters, 3, 3, 3, 1. Can you picture that? It's a group of 10 units divided into 3, 3, 3, and 1 without having to read each number aloud, just by observing the clusters. And in that way, counting the lines of text became possible. While practicing with the newspaper, I was also mentally counting each second. And the amazing thing was that I could perform an impressive trick, declaring for 48 seconds, that's exactly 1 minute. And the number of lines I counted was 67. Isn't that astonishing? I've discovered countless other interesting things. I can read while yes, that's right. Yes, I can read perfectly normally, counting and grasping the main content simultaneously, but there's one thing I cannot do: talk. Why? Because when I'm counting, I usually talk to myself in my mind, so I can't produce external sounds. I'll murmur 1, 2, 3 as if I'm having a conversation in my head. One morning when I went down for breakfast, I met John Tukey, a renowned mathematician at Princeton at the time. We had many interesting discussions. I shared with him my unique experiments and the abilities I possessed. After listening, he exclaimed, "That's absurd." He wondered, "I truly cannot understand why you would encounter any difficulty in communicating." Can you imagine? I was completely stunned when I saw that he could read. No matter how unbelievable it sounded, we decided to proceed with calibrating him. Would the results surprise us even more? Do you know how long it took him to count to 60? About 52 seconds or something close to that. What does this imply? Although I don't remember the exact numbers anymore, after he finished, he just casually said, "All right, are you curious about the next reaction?" And then he confidently asked, "What do you want me to say? Mary had a little lamb, I can talk about any topic." What does this reveal about his abilities? And so the story continued. 52 seconds, almost a minute, and astonishingly he did it perfectly. How did he manage that? While I was completely unable to do it, he asked me to read. Why? Because he couldn't believe what he had just witnessed. And then as we started comparing our notes, a surprising truth was revealed. When he thought about counting, it wasn't sounds in his head, but the image of a tape reel with numbers clearly visible. Strange, isn't it? With each click, 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 that virtual tape reel would advance, revealing the clearly printed numbers on it. Can you visualize that? He could actually see those numbers in his mind. And here's the key. Because he was using an optical system to count rather than relying on speech, he could talk as much as he wanted. What does this mean for us? But there was a limitation. If he had to read, looking at his watch was impossible. Why was that? Meanwhile, for me, everything was completely the opposite. And it was at this moment that I discovered an astonishing truth. Even in the simplest act of counting, there's a vast difference in how our brains operate, even though we think we're doing the same thing. Have you ever wondered what's truly going on in someone else's head? And so a thought suddenly struck me. If this difference holds true even at the most basic level, then as we delve deeper into the complex world of mathematics with Bessel functions, exponential functions, electromagnetic fields, and countless other abstract concepts, could the images and methods that we use to store and process information, along with how we think about them, be the very factor determining success or failure? Do you think so? What if we could fully understand each other's ways of thinking? We would be able to explain why sometimes one person struggles immensely to grasp something that's as clear as day to you, and vice versa. Could it be that translating what you just said into someone else's unique thought framework is no easy task? It sounds like I'm talking like a psychologist, doesn't it? But honestly, I have absolutely no specialized knowledge in this field. So what made me think this way? Just imagine, what if the smallest things behaved completely differently from anything large and familiar we've ever known? Because you see, as animals and their brains evolved, they adapted to process information under normal circumstances. So can our brains truly comprehend those abnormal things? But if the most fundamental particles deep down follow entirely different rules and properties, behaving unlike anything we see on a large scale, then can we truly understand and visualize the nature of reality? Is this the reason for the universe's greatest mysteries? So what is the real challenge holding us back? Have you ever wondered how things work at the microscopic level? It's miraculous. They are incredibly different, completely opposite to how everything operates on a larger scale. Do you think electrons are merely wave particles? No, not entirely. So are they just material particles? No, that's not entirely true either. Or are they just a fuzzy cloud surrounding the nucleus? No, that's not entirely accurate either. But if you truly long for a clear vision, a deep understanding, a true sharp picture of the atom so we can fully comprehend exactly how it operates. In other words, what we crave is a perfect picture, a truly profound insight into the nature of reality. But how can we achieve that? Because that image must be expressed entirely in the language of mathematics. The interesting thing is that we have a mathematical expression, a formula so incredibly strange, isn't it? It's perplexing. But we can still write down mathematical expressions and accurately calculate the behavior of objects, even if we can't visualize them intuitively. Imagine this, it's like a computer. You input numbers, and with the available formula, you'll know exactly when the car arrives at different destinations. That machine simply performs calculations to determine arrival times, but it cannot visualize the car itself. Strange, isn't it? It simply calculates. Similarly, we know how to perform calculations, but we cannot visualize the object. So what does this mean? No, that's not 100% true, because in some specific situations, an approximate image can still be useful. Interestingly, visualizing it as a cloud surrounding the nucleus, which when compressed creates repulsion, is very effective in explaining material stiffness. Does that surprise you? Meanwhile, treating it as a wave helps explain some other phenomena effectively. Are you curious what those phenomena are? All right, so when we consider specific aspects of atomic behavior, such as temperature, what does it mean to treat them as just tiny balls? This approach is good enough, and it provides a very intuitive, very easy to visualize image of temperature. Don't you agree? However, if you delve deeper, asking more specific questions, such as, how is it that when helium is cooled to absolute zero, where there is no longer any motion, it becomes a perfect liquid with no viscosity, no resistance, flowing perfectly without freezing? Have you ever wondered how to visualize an atom with all its complexities? Unfortunately, I must confess that it's beyond my capabilities. What I can do, however, is thoroughly explain why helium behaves the way it does. How? Simply by applying my equations and deeply analyzing their implications. Interestingly, helium will behave exactly as we observe, confirming that our theory is perfectly accurate. So where's the problem? We still can't create accompanying visual images to illustrate that theory. Is this due to a limitation in our abilities, preventing us from grasping appropriate visual images? Or, in reality, are there no correct images at all for those who constantly try to visualize everything based on what's familiar? In my opinion, the latter is more likely. There are no truly suitable visual images if we keep clinging to what's familiar. So can we train ourselves to become accustomed to the unfamiliar? For instance, through deep study of atomic properties and quantum mechanics, or by persistently practicing with equations until they become second nature, just like you instinctively know that two colliding balls will shatter. You would never say that two colliding balls will turn blue, right? Because you already know what their outcome will be. So the big question is, will future generations, as they develop, achieve a deeper understanding of how things work compared to us today? Will they be able to create new teaching methods and approaches that help future learners grasp complex perspectives and become so well trained that they no longer face the same difficulties we do when trying to visualize an atom? Surprisingly, there's still a school of thought that adamantly refuses to accept that atomic behavior could be so different from what we observe on a macroscopic scale. In my opinion, this is a deeply ingrained prejudice stemming from our overfamiliarity with how things behave on a large scale. They relentlessly search, patiently waiting for the day we discover that deep beneath quantum mechanics, it's still just ordinary colliding balls or familiar moving particles. But I believe that effort will not succeed, because nature's imagination is vastly greater and richer than anything humanity can conceive. And that very fact will never let us rest easy in our limited understanding.